Hello. So, today we start with formal introduction of finite elements per se, using finite elements to solve a problem of engineering analysis. And we begin with the simplest of all, the finite elements of one dimension, that is only one coordinate dimension is enough to describe the problem at hand. So, many problems of engineering analysis can be adequately modeled with only one independent variable, and that can be described by one coordinate direction. Now, there are so many problems. The simplest class of this problem is defined by a second order differential equation, similar to what we had seen earlier regarding describing the axial deformation of a bar or a heat conduction in a rod, or it can also describe transverse deflection of a taut cable, or it flow through porous media, or even electrostatics and several other problems. The general structure of the problem is same, and it is only the interpretation of various terms, various elements of the equation that are that keep on taking on new interpretation depending on the field of application. But mathematically the problem remains of same class second order differential equation. The domain is a straight line along one coordinate direction, and therefore, the domain decomposition, as we discussed about the problem of finite element, the concept of finite element, that we define the total domain of the problem as uh, assembly or as union of several non overlapping subdomains or finite elements. So, when the domain itself is a straight line, then subdomains are merely line segments uh, of part of those part of the given straight line. So, if the length of the bar that we need to model is of L 0 to with x coordinate ranging from 0 to L, then we can divide this domain of problem domain into several smaller subdomains of different lengths as the need may be. And the interpolation model uh, that we discussed earlier, the primary variable of the problem needs to be approximated, and we adopt interpolation model, and interpolation model for primary variable can be easily developed for one dimension and knowing the geometry. How that is done we will see in a short while. Now, polynomial interpolation, obviously it degree of polynomial depends on how many terms are there, how many independent terms are there. So, a linear polynomial requires two terms, constant term and a first degree term, and it requires there are two unknown coefficients, and obviously for to know to define two unknown coefficients we need two constraints that can uniquely define this variation, and therefore, there are two nodes of interpolation that is required to that will be required to define a linear variation. Similarly, a quadratic polynomial will have three unknown coefficients, constant term, linear term and a quadratic term, and these three unknown coefficients can be evaluated by using three constraints, and those three constraints are provided by the function values for interpolation at the nodes. So, there will be three nodes for quadratic interpolation, and similarly for cubic. So, these are the possible possibilities that we can have for one dimensional interpolation. So, for a linear interpolation we will need two nodes for interpolating between these two values at the nodes, function values at the two nodes. For quadratic we will need function values at three nodes, and for cubic variation we will need the function values at four nodes, and a unique polynomial variation of a desired degree can be determined by imposing these constraints at these nodes of interpolation. So far so good. So, nothing better than introducing a concept by through an example. So, let us consider the solution of familiar differential equation, second order differential equation, which can define as we said uh, axial deformation in a bar or tension transverse deflection of a cable under tension or heat conduction and so on. So, we have this ordinary differential equation, second order differential equation, the domain given by 0 to L total domain, and there are two boundary conditions. One is at x is equal to 0, we have essential boundary condition, the function value is defined to be phi 0, and at x is equal to L we have a boundary condition that is prescribed on the secondary variable of the problem that we will see, and that is at the other end of the domain. So, the domain is defined by two endpoints. So, it is a 2-point boundary value problem that we are looking at. Now, if we have to find the approximate solution, so basic unknown function, we need to find the solution for this unknown phi. So, if that is approximated by let us say phi hat, then obviously there is going to be some error in the differential equation and boundary condition. So, the weighted residual statement, the strong form of weighted residual statement, that is we just substitute the approximation in the governing differential equation and the boundary condition and collect the terms. So, that is the strong form. So, this first term is the domain residual weighted statement of domain residual, and this is the boundary residual term. I am not expanding on the boundary residual term at the moment. We will be concentrating on the domain residual term for development of finite element approximation. So, if we perform the develop the weak form of the weighted residual statement from this expression, it is just one step of integration by parts of this first term. If we integrate by parts by this first term, then we will have this boundary term, and the transfer, this derivative will get transferred onto the weighting function. Rest of the terms are exactly identical, just expanded it. So, we are not touching any of these. So, now we look at this weak form. Now, obviously we discussed that the reason why this is called a weak form is the higher order highest order derivative is decreased, while the strong form statement of the strong form had the second order derivative as the highest order of derivative on the approximating function, approximate solution phi hat. The weak form, the highest order derivative on the approximation is only first order. So, the approximate solution need only be differentiable up to first order, and it can still be considered as a valid approximation. So, obviously that will have some implications on the smoothness and the derivative requirement, etc., but we will see it can be it can lead to very useful approximation, and the approximations can be improved as progressively. Now, looking at the boundary term, we again take recourse to this boundary term and interpret or try to identify what are the secondary variables of the problem and what are the primary variables of the problem. Now, primary variables of the problem, the weighting function term, and we replace that is W. So, W are presents itself in its own form without any derivative on the boundary term, in the boundary term of weak form, and we replace W by the unknown of the problem, that is phi. So, that phi becomes the primary variable. So, primary variable of the problem is the unknown function phi, and this is the coefficient of weighting function in the boundary term, that is the secondary variable, and therefore, boundary condition on the secondary variable, this is the natural boundary condition at x is equal to L. Boundary condition imposed on the primary variable, that is phi, at x is equal to 0, this is the essential boundary condition of the problem. Now, as we saw, the primary variable is phi, and the approximation phi hat uh, has to be developed as an interpolation between the values of phi, the values of primary variable at the nodes which define finite elements. So, finite element we will come in a little while. We just saw in the previous slide, there are different types of finite elements, one dimensional finite element which will have linear variation, quadratic variation and cubic variation. There will be, for linear variation, there will be two nodes which define the extremes, nodes at the extremes of the element, and that define the subdomain which we refer to as finite elements. For quadratic variation, there will be one mid-side node in addition to extreme nodes, and for cubic there will be two internal nodes in addition to two extreme nodes. So, interpolation in terms of phi. So, if we interpolate in terms of primary variable, then the approximation phi hat that we are developing over each of these subdomains, as we will see, the continuity is ensured, continuity of phi is ensured, because there is a node which is common, the elements, adjacent elements, they share common nodes, they share common boundaries. So, the variable of interpolation is common in that case, and at interpolation model of approximation, as we know, the function value is retained. So, for one element on the left hand side of a node, we have some function value, and the same function value is enforced for the element on the right hand side of the node at the common node, and therefore, the function value is common, and therefore, the approximation remains continuous. So, the and that is what we call as 0 continuity, C0 continuity. So, 0th order derivative is continuous, is guaranteed to be continuous across the element boundaries, and therefore, these elements that we will be discussing, they are also referred to as finite elements for C0 continuity. C0 continuity refers to the case where the 0th order continuity on the function of approximation, the primary variable of approximation phi, is guaranteed. So, highest order of derivative in the weak form is 1, and that implies that approximation should be a complete polynomial at least up to first degree. So, this first order derivative should exist, and the only way it can exist is that it should, approximation should have at least one, at least a linear term, only then the first derivative will have some value. But that said, it is required that approximation should be complete up to required degree. So, that means it is not enough, it is not acceptable just to have one term approximation of linear first degree. It should, approximation should keep on building up from the lowest order degree. So, starting from the constant term. So, constant terms at 0th degree and then the linear term. So, that makes the complete approximation, complete polynomial. So, all the lower order terms in the approximation, they should have a representation in the approximation that we develop. So, if the highest order requirement is first derivative, then first derivative should exist, and that means the linear variation is indicated, and that implies a constant term should be there and a linear term should be there, at least at the minimum. So, a first degree interpolation, polynomial interpolation within a subdomain, and that requires two nodes with one value of primary variable phi at each node, and then the interpolation model, as we have seen, becomes, so phi hat within that element, the variation of the unknown function phi can be given as the interpolation model. So, phi 1 n 1 plus phi 2 n 2. So, where 1 and 2, these are the nodes which represent the extreme nodes of the element, defining the element domain, subdomain, and n 1 and 2, they satisfy the basic interpolation requirement, that is n 1 evaluates to 1 at node 1 and it vanishes at node 2. Similarly, n 2 evaluates to 0 at node 1 and it evaluates to unity at node 2. So, that the function approximation, when it is developed as this interpolation model, this function this approximation evaluates to phi 1 at node 1 and it evaluates to phi 2 at node 2, and in between it is an interpolation linear variation between phi 1 and phi 2. So, this linear variation can be a general polynomial, it can be as a general polynomial expression, it can be represented as a two term polynomial, that is one a constant term and a linear term. So, that is the basic representation. So, these are two alternate representation of the same variation. A polynomial, first degree polynomial is a first degree polynomial. There can be various ways of representing it, but essentially the polynomial variation is unique once it is defined. So, the first degree polynomial is unique between 2 points. So, continuity of zeroth order derivative is preserved across the element boundaries. So, for one element we have this approximation and for the next element we will have similar kind of approximation. Those are independent approximation, except that they will have adjacent elements will share node in common, and once the node is shared, the function value is preserved at that point. So, the continuity of zeroth order derivative in this particular model of approximation is preserved across the element boundaries, and this is referred to as C0 continuity. And approximation phi hat is piecewise continuous. So, it is continuous over an element, it is continuous over the next element, in between the boundary between these two elements, the function value is continuous. Function value is compatibility of the function, compatibility of the approximation phi primary variable is retained, but the gradient may not be, there is no constraint on the gradient. So, the gradients may differ. So, the function approximation, the derivative of the function approximation at for one element might be something, and for some other element just to the right of the node might be something else. So, that is fine. So, that is why we call it piecewise continuous over the whole domain. So, total domain, it is continuous over each element, and it looks like an assembly of piecewise continuity and making up the whole domain. So, this is what the problem what we were hinting at. So, total problem is defined by this domain 0 to x ranging from 0 to L, and boundary conditions defined phi is 0 at x is equal to 0. So, that is the fixed support constraint, and phi is equal to phi naught. So, it can be some constant at this point, and at x is equal to L, this is equal to this is the boundary condition imposed on the secondary variable of the problem. Now, this is the physical system, I mean physical system, that mathematical model which defines a physical system. This first needs to be translated into a finite element model, and finite element model requires domain decomposition. The first step to development of finite element model is to find out how many domains do we need to divide it into, and that is what we do here. We divide it into 4 elements. So, these are the in square boxes, these refer to the element numbers. So, subdomains or finite element numbers. So, this is finite element number 1. So, defined by nodes 1 and 2. These are the node numbers, that they are numbered sequentially, so that all nodes positions can be identified without any ambiguity. So, each node is defined by its coordinate. So, node 1 is defined by coordinate x1. So, that is x1 is equal to 0 in this case. Node 2 is defined by the coordinate x2. X2 can be some value, let us say L by 4, and node 3 is defined by coordinate x3, which will be some value, let us say L by 2, and node 4 is defined by the coordinate x4, which is maybe 3 L by 4, and node 5 is the end point. So, that is x is equal to x5 is equal to L. So, element 1 is defined by these two nodes, node 1 and node 2, that is all. Element 2 is defined by node 2 and node 3. Element 3 is defined by node 3 and node 4. Element 4 is defined by node 4 and node 5. So, now it is a you can possibly see a highly structured arrangement here. If I know the element 1, if I know that it is all I am decomposing or this domain into smaller subdomains of similar type of elements. So, let us say 2 node element. So, each of these elements, each of these 4 elements is a 2 node element. So, taken individually I only need to define 2 nodes which will uniquely define the element. So, and the nodes themselves are defined by the coordinates. So, it is a very structured system of information that that makes it very convenient to computer programming and automatic computation. So, this finite element model eventually leads to what we call as connectivity array or mesh, finite element mesh. So, that data, that connectivity array or the mesh data involves specification of which element is defined by which nodes, and nodes are defined by their coordinates. So, finite element 1, element 1 will be defined by x1 and x2. So, these are the coordinates of the nodes 1 and 2. Element 2 will be defined by nodes 2 and 3, and which are defined by, which are specified by their coordinates x2 and x3 and so on. And in a generic sense, it is the same type of element. So, that is being repeated all over. So, the only thing that is changing here is the coordinate of the nodes, but otherwise the character of the element remains the same. It is 2 noded element, and the variation is 1 degree, first degree polynomial, that is approximation. So, the variation of the primary variable phi within an element E, generic element, that is what we are looking at. If we isolate this one element here, which is let us say element, let us call this generic element E, which is defined by 2 nodes, then the approximation is within that element E is given by interpolation model phi 1 n 1 plus phi 2 n 2. So, this is what the interpolation model is, and if I arrange it in matrix form, this is what it will look like. And this is of course a linear polynomial. So, complete linear polynomial, again I a0 plus a1x. So, if I rearrange it into a matrix form, and this is what that will look like. Now, this has to satisfy the interpolation condition, that is at x is equal to x1, that is the first node of the element, the approximation has to agree with phi 1. It has to yield, the approximation should evaluate to phi 1. Similarly, at x is equal to x 2, the approximation should evaluate to phi 2. That is the condition of approximation as an interpolation model. So, if we impose that, polynomial approximation should evaluate to function values at the nodes of interpolation. So, phi 1 should be equal to a 0 plus a 1 x 1. So, this polynomial variation when evaluated at x 1, I should get the value of function at node 1. Similarly, phi 2 should be equal to a 0 plus a 1 x 2, and this gives us the basic condition for evaluating the unknown coefficients a 0 and a 1 for the polynomial approximation within the element. And because this matrix is known, the coordinates of the nodes are known a priori. That is how we decided the nodes when we discretized the domain, converted the physical problem into an assembly of finite elements. So, nodes are defined by their coordinates. So, these coordinates x 1 and x 2 are known to us, and therefore, this matrix can be inverted, and as long as the points are distinct, phi 1 node 1 and node 2, they are distinct points, then there is no way this will be singular. This inverse is guaranteed, and a 0 and a 1 can be identified by inverse of this coordinate matrix, and phi 1 phi 2 they are the function values. Now, this a 0 a 1 what we have evaluated, we can substitute here back in this equation polynomial approximation, and that leads us to the basic approximation of the problem, that is the polynomial variation 1 x. So, the constant term and linear term multiplied by these coefficients. So, this is what we get it, and then when we compare this with the first structure phi 1 phi 2, then we realize that the interpolation function n 1 and n 2 are essentially product of these two matrices. So, this is the polynomial term and this is the coordinate matrix, inverse of coordinate matrix. So, this is referred to as PC inverse. So, matrix of interpolation functions or shape functions as they are called, they can be derived as a product of polynomial terms P and C inverse, that is the matrix of coordinates. So, this is how we can generate the interpolation model. Now, these interpolation functions n 1 and n 2, they are evaluated. We know the functions given the coordinates x 1 and x 2. So, now all that we need to know is what are the coordinates, what are the 2 points which define the element, what are the coordinates of those points, and once I have the coordinates, I am immediately can work out what is the interpolation function for each of these 2 nodes. And once I work out this interpolation function for each of these 2 nodes, I can work out what is the approximation within that node. So, how this works in individual elements, I mean this exercise we need to do it in individual elements, and how this works out in the case of weak formulation. I mean we saw that in development of the weak formulation. Now, we will work out this over each element. We will take up this in our last lecture. We saw that the whole idea that this entire weighted residual statement which is defined over the entire domain, now we will consider it to be sum of residual statements over each of subdomains. So, we will look at this weak form over each of the subdomains. So, instead of talking about 0 to L, maybe we will talk about x 1 to x 2, that is all. So, the domain, the boundaries of the individual elements, and that is it. And from there we will develop the basic finite element level equations, and we will see how it looks like, and then we will see how we can use these element level equations and assemble them to build the complete whole domain equations. So, that is what we will discuss in our next lecture. Thank you.